All right, section 3. We should be in pretty good shape here, I believe. We're going to have to review logarithms a little bit, and we're going to talk about, most of you have calculators that we can put log whatever base we want in. If you've got an 84, you can put whatever base in. Anybody working on 83s still? No problem. We're just going to use ln. I'm going to show it both ways for that. Okay, an exponential function. I can understand why people might get confused on this. Exponential function. X to the 15th is not an exponential function. The exponent has to be a variable. Now it's exponential, a to the x. That's an exponential function. The base is said to be a. If you were to forget these rules of exponents, it's pretty easy to come up with them on your own. Oh, I forget. Do I multiply x and y? Sometimes I memorized it, and when I memorize things, I forget. So sometimes I add them, sometimes I multiply them. Well, if you were just to write a to the second times a to the third, you could rewrite that as a times a times a times a times a, and clearly that is a to the fifth, so we know our rule. Likewise, rule 3. I don't know, do I add, do I multiply, do I take the exponent to the power? Well, if I wrote this as a to the second to the third, I could write that as a times a times a times a times a times a, and I realize, oh yeah, that's a to the sixth. I multiply them. You don't have to write that down, but I mean, if it's helpful to you. How about this one, this rule? Oh, I subtract them here. I wonder why. Well, let's say we had a to the fifth on a to the second. I could write that as a on a. Two of these cancel two of these. Oh, of course. And I just always say this. Well, I've got 3 more a's in the top than the bottom. Okay. Rule 4. Let's say I had a b to the third. I could write that. That's not what I wanted. I'm sorry. Let's say I had a to the third, b to the third. I could rewrite that as a, b, b, b. I could rewrite that as a, b, because I can order my multiplication any way I want. And, of course, that's a, b, all of it to the third. But we know that. Likewise, we know if I had a on b to the third, that's just a on b times a on b times a on b, or a to the third on b to the third. Simple. You guys know these. All right, exponential growth and decay. Oftentimes population growth, half-life problems, investment problems, tons of real-world problems on these, and we were exposed to these last year. The function y equals k, we'll come back and talk about k, times a to some power, where k is greater than 0, is a model for exponential growth if a is more than 1. So in other words, if I have 1.7 here, every time I multiply by 1.7 k times, the number's getting bigger. If I have 0.5 here, the number's getting smaller. Every time I multiply by a half, it's dividing by 2. The number's getting smaller. Okay, that's exponential k if it's between 0 and 1, decay. Let's talk about k for a second, because very often this x is a t. It's time. And if time is 0, a is absorbed. So at time 0, y equals k. K isn't just any old value. K is our initial starting amount, assuming that time is starting at 0. Okay? All right, we'll take a look at that. All right. Let's say we were going to graph this by t-charting, and for some stupid reason, I just decided I'm going to start with x equals 2. Say we're going to do that. I want to see fingers for what my first value that goes with 2 is. After I add the 3, I want to see fingers. Come on. Watch this. Wrong, 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 wrong. Ooh, what'd you have? Wrong. Wrong. Tempting. Oh, negative 2 to the second is positive 4 plus 3, but this is not negative 2 to the second. This is the opposite of 2, the opposite of 2 to the second. Remember what I said about exponents last year? Exponents are lazy. This 2 is committed, or this x is committed to the 2, but not to the negative. If you put negative 2 to the x in your calculator like it appears here, it will tell you it is negative 4 and your calculator's right. Okay? Be careful with that one. So if I should choose 2 for some odd reason, then I get 2 to the second 4, the opposite of that, negative 4 plus 1, negative 1. 2, negative 1 is on there. But I might want to start with 0 instead. But even that would have caused us problems, I think. Because when we put 0, we'd say, oh, negative 2 to the 0th is 1, which is true. But the opposite of 2 to the 0th is negative 1. Plus 3, 2. All right? The calculator will take care of it for you, but if you're not using your calculator, careful. Let's put in 1. 2 to the first 2, the opposite of that, negative 2 plus 3, 1. So at 1, I'm up 1. Let's go to 3. Put in 3, I get 8. Negative 8 plus 3, 5, and I start seeing this thing's starting to move. Negative 5, excuse me. 3, 1, 2, 3, 4, 5. And I believe this. I know enough about exponential curves. I believe my next one's going to take me out through here. I always like kind of making a little exit mark. I'm going out before I get to that next tick mark so I don't get lazy. So I'm going to come down through here. You could put 4 in there and try, and you'd see. And I'm exiting there. All right. Let's go backwards. Negative 1. 2 to the negative first is 1 on 2 to the first is a half. Negative a half and 3 is 2 1/2. And I say, oh yeah, we're getting flat, pretty dramatically flat here. So I'm going to ask this question. If I put negative 100 in here for x, that's 1 on 2 to the 100th. 2 to the 100th is enormous. 1 cracker to feed a gazillion people. This is going to try to be 0, right? It's going to try to be 0, negative, but it's from the negative side, but it's going to try to be 0. It's never going to get to 3. It's going to get close fast. It's already pretty close. So 3 is like our exit here. And we just hug along it and just try to make the curve fit. Okay, so we definitely have an asymptote at y equals 3. Exponential functions, if there is no plus or minus afterwards, the x-axis is a horizontal asymptote. Okay. State its domain. Domain from left to right. Is it going to exist forever? Can I put 1,000,000 in here? Yeah, I can. It's just going to be really, really steep when I get there. So the domain is all reals. I think the book's doing the negative infinity to infinity thing on that. Does that sound right? Maybe we'll end up adopting that. Range, scan from bottom to top, it exists at negative infinity up until I get to 3 almost. Negative infinity up to 3 almost. Intercepts. Here's one. 0, 2. Here's another one, not as convenient. But what do I know about that intercept? I know it is something 0. So I need to know when y is 0, if I have 0 equals the opposite of 2 to the x plus 3, I'm going to add 2 to the x plus 3, or 2 to the x equals 3, excuse me. Do that again. 2 to the x equals 3. How do I get out of that guy? I'm going to go up here where I got lots of room. 2 to the x equals 3. Logarithms, right? Logarithms. I could go log base 10. I could go ln. If I had a calculator that could do any base I wanted, what base would I choose? What's the base of the exponential function? 2. I would choose, if I could, log base 2 on both sides. All right, this one's always fun. A logarithm is an exponent that turns its base into its argument. This is the exponent that would turn 2. This guy right here is the exponent that would turn 2 into 2 to the x. What could it possibly be? 2 to the what equals 2 to the x? It's just x, right? Or you can pull the x out in front. What's the exponent that turns 2 into 2? 1. X times 1. So this is x equals log base 2 on 3. Now, for those of you who are going to need to use ln or log, we would just do this. ln of 2 to the x equals ln 3. Pull the x out in front. X ln 2 equals ln 3. And ln 2 is just a number. If this was 7 times x, I'd divide by 7. So x is ln, not 3 divided by 2, but ln 3 divided by ln 2. Okay. Likewise, could have done it with plain old log. Questions there?
Do you want us to put it, like after we have that, do you want to plug it in our calculator, or if we just put ln3 over ln2 in a...
It depends. Depends if you're asked to round. A lot of times you just want exact values. Okay. I would say if it didn't specify and it wasn't a story problem where you could interpret, I'd say this is a better answer. Either of these two. You know, you're not going to be faulted for, oh no, that's just way too exact. That's way too correct. You know what I'm saying? Yeah. All right. Let's do this one. Let's say we didn't have a calculator. Stinks having to work with E. E, I'm just going to say E is approximately 2.7. We don't have to be that exact because we're putting it on a graph anyway, and they're not going to know whether it's 2.7 or 2.71 or what. So we're going to say it's about 2.7. Guess what value I'm going to choose first for X? There's only one that's really easy. Right. 0. So e to the 0 at the 0 or is 1 times 3, 3 minus 2, 1. 0, 1. Right? E to the 0th is 1 times 3, 3 minus 2, 1. All right, I'm going to go to negative 1 just so it becomes positive 1 here. That is e to the first, about 2.7, times 3, about 8.1. Minus 2, about 6.1. There's some error in there. Negative 1 gets me up 1, 2, 3, 4, 5, 6. Here's the good news. I think it's going to grow fast and just jump off the table after that. What's my horizontal asymptote? Were we listening? Up here? We talked about this? Let's think about it then for a second. As x gets huge, if I put 100 in here, this is 1 on e to the 100th, virtually 0, times 3, virtually 0, minus 2, virtually negative 2. We're going to get close to negative 2. Man, that gives me a pretty good idea of what my curve looks like, but I'm still going to battle for this one more point. Put in 1. I get 3 on about 2.7, right? Minus 2. And I would just say this, a little more than 1, right? It's a little more than 1, so at 1, I'm a little more than 1, and then down 2 from there, down 1, 2. We got a point right in here. Pretty close. So off the charts, down and through. Okay. We got a value here. We could set this equal to 0. Y 0. 0 equals 3e to the negative x minus 2. And we could solve that as we solved above. Add 2, divide 3, ln now, right? Base e. Is that right? Dot, dot, dot. We got an intercept at 0, 1. Okay, rewrite the exponential expression to have the indicated base, base 3. How convenient. 9 is a base 3 number. This is 3 to the second to the 2x. Or 3 to the 4x. Simple. What's harder is when they don't tell you what base to use. No idea why that wasn't there. I'm going to guess that's base 2. So this could be 1 on 2 to the third to the 2x, but 1 on 2 to the third is the same as you can say it. 2 to the negative third to the 2x, so 2 to the negative 6x. Okay. Like a bunch of those, I suspect. Compared to 55 and 56 today, a lot easier. Find the zeros of the function. Zeros of the function just means 2 to the x minus 5. When does it equal 0? It doesn't mean put 0 in for x. It means when is the function? When is f 0? Simple. Is that all right? 2 to the x equals 5. And now we're either going to ln if we've got an 83, or if we've got an 84. Can you get to the log thing on your 84s by going math, alpha, math? Have you tried that on your 84? Just go math, alpha, math. Does it get you there? It's kind of a nice shortcut, especially one to remember during here. So if I go log base 2, I just get in one step x equals log base 2 of 5. If we go ln's, here's where you should end up. X equals ln 5 on ln 2. How did I know that so quickly without going through it? Change a base formula, right? Log any base of 5 over log any base of 2. But you should be able to arrive at that. We okay, those of you with 83s? Okay. B, same problem. 3 to the x minus 0.5 equals 0. 3 to the x equals 0.5. Tell me what we know about x right now. What kind of number is x? It's a negative number, isn't it? Yeah, this has to become like 1 on 3 to the something. So same deal here. If I go log base 3 of that and log base 3, we got it. So that would be x equals log base 3 of 0.5, or if you were ln'ing, ln 0.5 on ln 2. Careful, not ln 0.5 on 2. ln 0.5 on ln 2. Good there? You can get on 3. That's why I got funny looking faces at me. On 3. Thanks. I think I was looking up at the one above. Thank you. Number 4. Population in Knoxville is 500,000 and is increasing at 3.75% each year. Approximately when will the population reach 1 million? I want it to end up at 1 million, but my starting value is 500,000. Here's my rate of change, and I don't know how long it's going to take. I'm going to call it T. The common mistake is to put 0.0375 in here. If you do that, you're telling these 500,000 people they die, but the people who move in or are born in are going to be okay. These people come back too. So it's 1 plus 0.0375 or 1.0375. When I distribute to the 1, I get all those 500,000 back plus the additional each year. Time for logarithms? Not yet. You can do it, but you got to use some. You're making your work a lot harder. I want to isolate the exponential. Divide by 500,000, and I get 2 equals 1.0375 to the t. Is that all right? Which, if you consider there's really could be a 1 in front of here, means the same time it would take a town to grow from 1 to 2 is the same time 500,000 to 1 million. It makes sense. All right, so if you've got the calculator, you could go log base 1.0375, log base 1.0375. Otherwise, you're going to end up with ln of 2 on ln of 1.0375. Let's make certain that we end up with the same answers regardless how we're doing it. So this would be t equals. If you got the calculator that handles that, great. If not, let's go with that guy. I don't know if you can see that very well. I get to 3 decimals, we'll go. I get 18.828 years. Does that sound right? Okay, one thing I want to point out on these types of problems, these real world ones, when you have an exponent in the variable and you make a mistake setting it up, usually the answer makes no sense whatsoever. It'd be like 74 trillion years, or negative 514 years, or 0.00013 years. Take the time just to look. If I was just getting 19%, or 19 years, excuse me, of like 4%, that's like 76% with no compounding, and that's at least reasonable. I need 100% gain. So, okay, I'm going to stop it at that point. We will wrap up the remainder of this on the next video.